Welcome to an introduction to basic absolute value equations and absolute value inequalities. Let's first review absolute value. The absolute value of a number is a number's distance from 0. So for the absolute value of 2, since here's 0 and here's 2, this distance here will give us the absolute value of 2. And notice how this distance is equal to 2 units, and therefore the absolute value of 2 is 2. Because the absolute value of a number is a number's distance from 0, we know distance cannot be negative. Next we have the absolute value of negative 2. Well, here's negative 2 and here's 0. This distance will give us the absolute value of negative 2. And once again, notice how this distance is equal to 2 units, and therefore the absolute value of negative 2 is also positive 2. And now let's consider absolute value equations. Here we have the absolute value of x equals 2. The solution consists of all the values whose distance from 0 is equal to 2 units. And we know from example 1 there are actually two numbers that have a distance from 0 equal to 2. X can equal 2, or x can also equal negative 2. So this absolute value equation has two solutions, x equals 2 or x equals negative 2. Next we have the absolute value of x equals 3. So now we're looking for all the numbers whose distance from 0 is equal to 3 units. So looking at the number line, if this is 0, notice how 3 is 3 units from 0, but negative 3 is also 3 units from 0. So once again we have two solutions to our absolute value equation. X equals 3 or x equals negative 3. Next we have the absolute value of x equals negative 4. So we're looking for all the numbers whose distance from 0 is equal to negative 4. But again, we can't have a negative distance, and therefore there are no solutions to this equation. Now let's talk about absolute value inequalities. Let's first consider the absolute value of x less than 2. The solution set for this inequality will be all the numbers whose distance from 0 is less than 2 units. Let's begin by listing some of the numbers whose distance from 0 is less than 2 units. For example, 1 is less than 2 units from 0, and so is negative 1. 1.5 is also less than 2 units from 0, as well as negative 1.5, and so on. So if we think about this, all the numbers whose distance from 0 is less than 2 units would be to the left of positive 2 and to the right of negative 2. We would not include 2 and negative 2 because the distance has to be less than 2 units, not equal to 2 units. So if we start at 0, we could go right 2 units, out to 2, but not include 2, so we'd have a rounded parenthesis here. And then going back to 0, we could go to the left 2 units, all the way out to negative 2, but not include the endpoint, so again we'd have a rounded parenthesis here. This would be one way to graph our solution set, or using open or closed points, we'd have an open point on 2, an open point on negative 2, and graph between the two values. These two graphs are equivalent. This is our solution set for the absolute value of x less than 2. Now notice how it doesn't ask, but if we did want to express this using interval notation, we'd have the open interval from negative 2 to 2. Again, we don't include the endpoints, so we have a rounded parenthesis on the left as well as on the right. Next we have the absolute value of x is less than or equal to 2, which means now we want all the numbers whose distance from 0 is less than or equal to 2 units, which means all the values listed here would also be in the solution set for this inequality: 1, negative 1, 1.5, negative 1.5. But because of the equal part of the inequality symbol, we could also include 2 and negative 2. And of course, this list would continue. So to graph our solution set, again, if we start at 0, we can go to the right 2 units. And once we reach 2, again, this time we include the endpoint of positive 2, so we could use a square bracket. And then going back to 0, we could go left 2 units from 0, all the way out to negative 2. And again, we include negative 2 this time, so we have a square bracket. Or using points, we'd have a closed point on 2, a closed point on negative 2, and graph between the values. This interval includes all the values that are less than or equal to 2 units from 0. All the values to the left of positive 2, including 2, and all the values to the right of negative 2, including negative 2. Using interval notation, this would be the closed interval from negative 2 to 2. So we use square brackets indicating the endpoints are included. And then finally, in our last example, we have the opposite value of x greater than 2. So now we want all the values whose distance from 0 is greater than 2 units, which should be all the values to the right of positive 2 or all the values to the left of negative 2. So if we wanted to list some of these values, we have an infinite number of choices, but let's say 2.5 has a distance from 0 that's greater than 2 units, as well as negative 2.5. We could also say 3 or negative 3, and so on. Let's go ahead and graph our solution set. Notice how the distance can't equal 2, it has to be greater than 2 units. So if we start at 0 and we go out to the right 2 units, we don't include 2, but we do include all the numbers to the right, so we'd have a rounded parenthesis opening to the right, graphing to the right, approaching positive infinity, or going back to 0, we could go left 2 units. We wouldn't include this endpoint, so we'd have a rounded parenthesis here, but then we'd graph to the left. Or using open or closed points, we'd have an open point on 2, graph to the right, open point on negative 2, graph to the left. Now again, it doesn't ask, but if we wanted to express the interval using interval notation, notice how we have two intervals, one on the left and one on the right. And there's two common ways to do this. On the left, we're approaching negative infinity all the way to negative 2, not including negative 2, so we have a rounded parenthesis. Then we could say or. On the right, we have the interval from 2 to infinity, not including 2, and not including infinity. Instead of using or, though, sometimes you'll see a capital U, so we could also say negative infinity to negative 2, open on negative infinity, open on negative 2, union, open on 2, approaching infinity. Okay, I hope you found this helpful.